Hello, and we're going to talk today about antiderivatives. So, there's another word sometimes used for antiderivatives. I'm not going to say what that word is yet, because that would be a spoiler. We'll get there when we get there. So, what are we talking about then? Well, in the most general concept, we're saying a function is an antiderivative of f. So we'll use a capital F to represent the antiderivative of f on some interval, provided the derivative of capital F is equal to little f for every x in there. So we're just doing it backwards. We are saying, instead of taking a function, finding its derivative, we're taking a function and finding something that it is the derivative of. So this is a common concept in math. We have an operation, we want to invert it. So once we have multiplication, we then say, oh, let's find a number that we could multiply together to make that, and that's called division. Once we have squared, we say, let's find a number we could square to get this. That's called a square root, etc. Here, we define derivatives. We spent a month talking about all their properties. So now we're going to try to go backwards. So find an antiderivative of f of x equals 2x. Now that is, you likely have already figured this one out just in your head. What function has 2x as its derivative? Well, the answer, you might be shouting at your screen, is that f of x is x squared. And that is an answer, but it is not the only answer. If I tell you I'm thinking of a function whose derivative is 2x, maybe it's x squared minus 5. Maybe it's x squared plus 12. Maybe it's x squared plus pi to the e. No matter what, this is a constant, so derivatives of all these will be 2x. So we say the general antiderivative would be x squared plus c. This is another one of those arbitrary decisions. We use capital C to indicate that we are talking about some constant. Now, the question is, okay, that's nice. Is that the only way we can get an antiderivative? Is there someone that's not of the form x squared plus something? Well, no. We'll state this as a theorem. If capital F of x is an antiderivative, then if there's any other antiderivative, it can be written in the form fx plus c, where c is a constant. And so we could prove this if we say we'll have some function f, little f, and we'll say capital F and g, capital G, are both antiderivatives. Well, first off, if g of x is equal to f of x plus c, then little g of x, its derivative, would just be little f of x. So those are both antiderivatives. Can we prove that there's no other option? Well, that would require the mean value theorem, which we haven't really talked about. We'll talk about a little later in the semester if we get the chance. But let's say h of x were f of x minus g of x. So then little h of x will have to be 0, because if we take the derivative, it'll be little f minus little f. That's what we're saying. Capital F and capital G are both antiderivatives of little f, so they must both have derivative of little f. So what we can say is that if we have some interval from a to b, the mean value theorem says that if we did the derivative of h, there's some point where it's the same as h of b minus h of a over b minus a. And then, but h prime of c is got to be 0. So that means it must be h of b minus h of a over b minus a is 0. And we know that if a fraction is 0, then its numerator is 0, which means h of b equals h of a. So we could say f of b minus g of b equals f of a minus g of a. And if we rearrange that and we plug in, say, x into any of these instead of b, we would say then f of x minus g of x is equal to this thing, which is a constant. So when we subtract big F and big G, we get a constant. And since all we knew was that they're both antiderivatives, that must mean that's always true. That if you subtract them, you always get a constant. So you might not follow the proof, especially because we haven't really talked about mean value theorem in this class. Again, it's something that I think we'll get to. We'll just at the end of the semester. I'm not sure why it's put at the end of the semester instead of a little earlier, but regardless, the main point we want to say here is that f of x plus c is the only form of the antiderivative. So yeah, we can just take this as a given for now. If there is an antiderivative, and we know the form f of x, capital F of x, then it must be plus c is the other one. Or any other one. All right, so let's move along. Let's do some examples. Let's find some general antiderivatives of all of these. So I might recommend just go ahead and pause and try these on your own, and then I can show you the solutions. So what we would get here, if we have f of x is 3x, then f of x, capital F, would be, so we'll state the derivative rule in reverse. Raise the exponent by 1, divide by the new exponent. That'll be 3 over 2x squared plus c. The next one would be 2x squared. So we will get 2/3 x cubed plus c. Forgetting the plus c is a good way to lose points on a test. So just remember it, because everyone always forgets it. But you gotta say that it could be any antiderivative, not just one of them. There was a joke about that, well, I'll tell it later. It's not that interesting. 2x plus c. Because derivative 2x is 2. You can always check this by take derivative of the right and you'll get what's on the left. Sine of x. So I think back to how the trig functions worked. If I were taking derivatives, it was like this, right? Derivative of sine is cosine, derivative of cosine is negative sine, and so forth. So if we're doing antiderivative, we'll go backwards. So the antiderivative would be negative cosine of x plus c. Okay, what's next? X to the n, where n greater than or equal to 0. All right. So this is the power rule. We know the power rule for derivatives would be nx to the n minus 1. We're doing the opposite here. So in the opposite order, we first raise the exponent by 1, then divide by the new exponent. Okay? So let's do a few examples there. Notice it says n greater than or equal to 0. We'll talk about why that is in a little. X to the negative 3, so we raise the exponent by 1, becomes x to the negative 2 divided by negative 2 plus c. So yeah, all we're doing is working derivatives backwards. And if you're not sure, again, you can always just take the derivative of your answer and see if it gets you back to where you started. Let's do a few more here. Here's little f, here's capital F. So, square root of x, which comes to be written as x to the 1/2. So we would raise the exponent by 1, x to the 3/2, divide by the new exponent, 3/2, and a plus c. And then we probably want to rewrite that as 2x to the 3/2 over 3 plus c. Next one was secant squared x. Okay, now this is not power rule. Because, you could try to do power rule like secant third over 3, but the problem is, if we're doing a derivative of this, we'd have to do some sort of chain rule thing with it. And so, since we're doing an antiderivative, we figure there's also some sort of chain rule. And we will teach what that type of chain rule is a week or two from now. For now, though, I just recall derivative tangent is secant squared. So therefore, the antiderivative secant squared must be tangent. Last one is x plus 1 over square root of x. Remember, we're going to simplify this first. This is x to the 1/2 plus x to the negative 1/2. Now, some of y'all will do this and then circle that as your answer. This whole, I've got it written in another column to remind you that this is not actually derivative. All you did is simplify. Or antiderivative. We haven't done anything except rewrite the problem. So now we say, okay, we get x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 plus c. And then I'm going to rewrite this again. 2x to the 3/2 over 3 plus 2x to the 1/2 plus c. So those are just some basic antiderivatives. This is just drills. You have to go through and use the power rule. Since you know it for derivatives, it's maybe a slightly harder, but not much harder to do it with an antiderivative. Okay. What else do we know? Hide the whiteboard, that's in the way. All right, so let's look at the next. So here are some general rules that are worth knowing because they show up a lot. So we know the derivative of a constant is 0. And so therefore the antiderivative of 0 is a constant. If our function is a constant, its antiderivative will be a line. This is saying something has a slope of k, so the original function must be a line with slope k. Some of the basic rules from derivatives work the same way. These linearity rules. If we have two functions added or subtracted, we can just do their antiderivatives separately and then put a plus c. If we have a constant and we need to take an antiderivative, we just say it's the constant times the antiderivative of f plus c. So constants can be pulled out of derivatives. And then the power rule. Earlier I just said for positive n, but actually it works as long as n is not negative 1. We add 1 to the exponent, x to n plus 1, divide by n plus 1, and put a plus c. Why can n not be negative 1? That seems arbitrary. Well, let's consider what that would look like. If I did try to do that, x to the minus 1, the antiderivative would be x, raise the exponent by 1, divide by the new exponent. Oh, we get 1 divided by 0. So that's not defined. So weirdly enough, yes, that is the one case where the power rule doesn't work. Now, does that mean there is an antiderivative? Well, no, there is one for x to minus 1. They actually don't have us teach it in Calc 1. They saved that for Calc 2, but I can tell you what it is later if you're curious. Anyway, let's move on. So, let's find any functions g such that g prime of x is 4 sine x plus 2x a fifth minus root x for positive x. So I am going to split that up first. I'm going to split that into 3 functions. G prime of x equals 4 sine of x plus, let's see, 2x to the fifth minus square root of x over x. Let's split that into 4 sine x plus 2x to the fourth minus x to the negative 1/2. Then g of x, the antiderivative, would be negative 4 cosine x plus 2/5 x to the fifth minus 2x to the 1/2, because I raised it to make it positive 1/2, and I divided by that. Divided by 1/2 is the same as times 2. And then a plus c at the end, which might be cut off, but there, I hope that looks a little better. Yeah. Okay. So let's see the next one. Find f of x if f prime of x is x root x and f of 1 equals 2. Okay, that looks a little different. So what's with that f of 1 equals 2? Why are we telling me that? Well, it's kind of like if we were trying to find the equation of a line, we would want a slope and we want a starting point. Now our derivative, we know derivative kind of represents slope anyway. So we're saying if this is our slope here as x root x, and we also know a starting point, that would give us a line. Or since this thing, the slope is changing, it'll give us a specific function. So let's see this. F prime of x is x to the 3/2. Let's write it like that. F prime of x equals x to the 3/2, and f of 1 equals 2. So then, f of x must be, let's see, raise x by 1, so we get x to the 5/2, divided by 5/2, let's say it's times 2/5, plus c. So what this would look like if you were to put this on a graph, and I recommend this, go to like Desmos something now, and try typing in 2/5 x to the 5/2 plus c. And then it'll have you a little slider, and you can slide the c up and down to see what happens. But what it would give me would be something like, I don't know, something kind of parabolic. I'm not quite sure what the shape would be. Well, type it into a calculator real quick just so that I can, if we were in class, I'd put this on the screen on Desmos, but you can go ahead and do that on your own screen right now. Yeah, something like that. Kind of like a kind of parabolic, not quite, but a little steeper than parabola. But what we would get is a whole bunch of them that would all be kind of parallel. All these functions will have the same derivatives because they're all parallel to each other. So if you give me an x, they would all have the same slope there. But if we also know that it goes through this point, let's say 1, 2, then that tells me exactly which one we're dealing with. So how do we find the c? Well, it's kind of like what we do sometimes with finding the slope-intercept form. We plug in the numbers that we have. So f of 1 is 2. So when x is 1, 2/5 times 1 to the 5 halves plus c, we get 2. We kind of nailed down the x and the y temporarily to find the c. So x and y change, but the c doesn't. We get 2 equals 2/5 plus c. So then c is 2 minus 2/5, or 8/5. So therefore f of x is 2/5 x to the 5 halves plus 8/5. And so that is the only possibility we have that would give us the x to 3/2 as derivative and would pass the point 1, 2. Okay. So let's see what's next. All right, this one's a little different. This says f of x, we're given the second derivative. F double prime is 12x squared plus 6x minus 4. F of 0 is 4 and f of 1 is 1. And we're going to find the specific solution. They sometimes call this a general solution and a particular solution. So let's do that. All right, I have f double prime of x equals 12x squared plus 6x minus 4. I have f of 0 is 4. And f of 1 is... my screen's cut off here. Sorry about that. F of 1 is 1. All right, so I'm going to get some antiderivative here. So I want to find f. So let's go back to f prime. So this is the second derivative we're given. So we'll go back. This will become 12x to the third divided by 3, which would be 4x to the third, plus, raise the exponent 1, 6x squared divided by 2 would be 3x squared, minus, and then what has a derivative of 4? Well, that's 4x plus c. And now let's get f of x, then would be x to the 4th plus x to the 3rd minus 2x squared plus... Okay, well, it's constant, so its answer would be cx. But then we need to bring in another constant, which I'll call d. Or sometimes they call them c1 and c2, whichever. But the point is, these are different constants. And so if we only had one of these, these are called initial conditions, by the way. And this is this is basic differential equations, which is to say you're finding an antiderivative and then you're using these initial conditions to figure out the particular case. So this is the general solution, but now we'll use these constants to find the particular solution. So f of 0 would be, well, all the x would be 0, so that's just d equals 4. Okay, so d is 4. So f of x is x fourth plus x third minus 2x squared plus cx plus 4. I think we had to do the 0 first. If I did the 1, I would get 1 plus 1 minus 2 plus c plus d equals 1. And I have two equations, or two unknowns, only one equation. So I kind of have to do the 0 first. Sometimes they might not have anything eliminated, in which case you'd have two equation, two unknown, and you have to think back to algebra of how to solve those. Well, anyway, now that I have this, I can say, okay, I plug in the other one, f of 1, we know it equals 1, but we can plug it in, and it's 1 plus 1 minus 2 plus c plus 4. So I just replaced all the x with 1s. This would become c plus 4. 1 plus 1 minus 2. So then 1 equals c plus 4, so c equals negative 3. So our particular solution here is, let's just change that c to a minus 3. And that's it. And so if you want to double check, you would first say if I plug in 0, I get 1, or I get 4. Plug in 1, I get 1. And if I take the second derivative, I get to this, 12x squared plus 6x minus 4. All right, so let's do one last problem. And it's this problem about Mars. Gravity on Mars is about 3.71 meters per second squared. I looked this up. Olympus Mons, the tallest mountain in the solar system, is 21.1 kilometers. So let's say we have a cannon shoot from the summit of Olympus Mons at 40 meters per second, an angle of 30 degrees above the horizontal. So write a function for the cannonball's height after t seconds and figure out when it hits the ground. Now, we're going to assume the ground is flat. Realistically, for such a high place, you probably would have to include the curvature of the planet, but we're just going to hand wave that away to make it simpler. All right, so what do we know? Well, we know one simple thing then. The acceleration, that says gravity on Mars, technically I guess I should have said the acceleration due to gravity is negative 3.71 meters per second squared. And so we want to get a function for the height. Now, the acceleration is constant, so then we can get an antiderivative. The velocity, vertical velocity, v sub y, would be negative 3.71 plus a constant. Now let's think about what we are describing here. Here's this mountain. It's 21.1 kilometers high. We have a cannon here that shoots at an angle of 30 degrees. And we're not going to worry about how far it's going horizontally. We're just going to focus on the vertical distance. So, it was shot at a speed of 40 meters per second. Now, the acceleration, since the acceleration is all vertical, then we're using just a vertical velocity. You could do also horizontal one. There'd be no acceleration, that version. But we're just going to focus on the vertical. All right, so that means this cannon, it shot a vertical and a horizontal component. And so if you think back to your trigonometry, the hypotenuse here is 40. So that means the velocity here that it left, the vertical velocity that it left with was 40 times sine of 30 degrees. And sine of 30 degrees is 1/2, so this comes out to 20. So what this tells me then is that Vy at time 0 is positive 20. That is, when it leaves the cannon, its vertical velocity is 20 in the upward direction, while its acceleration is being pulled down. Should have put a T here a while ago. Hopefully someone yelled that out at me already, but there it is. So, if I plug in 0, I get 20. So this is 20 equals 0 plus c. So the vertical velocity here is negative 3.71 t plus 20. And so this plus c will actually always end up being the initial velocity if you're starting with these free fall problems where the only force is gravity. And then let's find the height. So the antiderivative of that would be height. This is vertical velocity, meaning change in height over change in time. So we do another antiderivative, be, let's see, 3.71 over 2 would be 1855. And it's okay to use decimals for this one because we're talking about a physical application. Plus 20t plus d, a second constant. I think you would have to have done, in the last problem, we got both constants and then solved for them. But that was because in the last problem, both constants were about the original function, in this case, h. Whereas in this here, one of our initial constants about velocity, so we had to use it at the velocity stage. And as for this one, what is the height at time 0? Well, it's... All right, let's be careful here. This is meters. Acceleration is meters per second squared. This thing is meters per second. We would need this to be in meters for it to make sense, so let's convert that to 21100 meters. All right, so if we plug in 0, those blank out, and we're left with h of t would just be negative 1.855 t squared plus 20t plus 21100. So if you work through the units, this 185 here is meters per second squared. You multiply by second squared, you get meters. This is meters per second. You multiply by seconds, you get meters. And this is just meters, so it's all meters added together. So that's our function for height at a certain time. Now we're also asked, when does it hit the ground? So set this equal to 0. Well, now this is an algebra problem. We use quadratic formula. Or there is another way we could... Well, no, there's not. I'm sorry. I was thinking of trying to find the max, which you could use derivative to set equals 0. But no, we're going to have to use quadratic formula on this one. So t would equal negative b plus minus square root of b squared is 400 minus 4ac. So it'll be plus 4 times positive 1855 times 21100. All divided by 2a, which was that negative 3.71. By the way, the general form for free fall is 1/2, or for any constant acceleration, 1/2 at plus v naught t plus h naught, or x naught, or position naught, whichever. So you may have seen this equation before in a physics class. This is where it comes from starting with constant acceleration, doing 2 antiderivatives. And then that's why in the normal freefall problem you'd see a 4.9 because acceleration is 9.8, so that's half of that. Now let's type this into a calculator. Excuse me. So we get square root of 400 plus 4 times 1.855 times 21100. Square root, store that as x. Negative 20 plus x divided by negative 3.71. It's out to a negative. And then negative 1 minus x divided by negative 3.71 comes out to 112. So I get 112 seconds. And I also got negative 101.4 seconds. You might, what is that about? Well, it's because our cannon is moving forward in time until it hits the ground. If we could reverse time and follow this parabola backwards, it would be the time when it would have taken off. But that's not relevant to this problem, so the answer is 112. All right. Thank you for watching. I'll see you in class.